Very much for the. Oh, okay. So yeah, thanks for the invitation. And yeah, my talk today is about filter definitions. And it's based on this paper that I have with George Jekyll and Michael Spanowski. And what we did here, we wanted to study filter definitions in the context of quantum field theory, but we noticed that most of the issues that arise can already be discussed at the level of classical field theory. So the paper is all classical field theory, and then we have some connections to quantum field theory. So let me start with some motivation. So as you may know, filter definitions are used many times in EFTs, in effective field theories, to simplify the Lagrangian. And I have a couple of examples here. So for example, in axion effective field theories, you typically redefine the fermion fields in this way, involving the axion field in the exponential, in order to eliminate some operators. And also in the standard model EFT, at dimension 6, for example, you simplify the Lagrangian by using the equations of motion. Typically, what you do is you take some operator that contains derivatives of the standard model fields and replace that derivative by what's on the other side of the equation of motion. This is justified by the fact that this is equivalent to doing a filter definition, but it only works at a fixed order in the expansion in the EFT. So for example, if you do this at dimension 6 and you don't care about dimension 8 operators, that's okay. But if you want to keep dimension 8 operators, then you need to actually do the filter definition in order to see all the effects that you have. So let me explain that in a little bit more detail. So let's say you have some filter definition with your original field phi and your new field curly phi related by, so there's a relation between the two through some functional f. We'll call this the redefinition. And it has this form. It's curly phi plus some small parameter lambda times an arbitrary operator. And you can have in here derivatives or higher powers of phi or whatever. So if you replace this in your action, then you get the original action plus a linear term that's proportional to ds d phi, which is the equation of motion for phi. So you can see that essentially you can change the action by an arbitrary operator proportional to the equation of motion, and you will get an action that's related to the original one by a filter definition. This is only at order lambda, and lambda here would be, in an EFT, would be 1 over the cutoff scale. So so if you look at higher order terms, so this would be dimension 6, for example, in the SMEFT. If you look at dimension 8, then you have extra terms, which are not proportional to the equation of motion. So this is the point that I was making about being able to use the equation of motion only up to linear order in the perturbative parameter. So, okay, so this is equivalent to doing a filter definition, but then there's the question, why are we allowed to freely use the filter definitions in order to simplify Lagrangian? And when can we do this? Because not all filter definitions that you can think of are valid in the sense that they will not give equivalent physics. So yeah, so the talk is about that. I've divided it in 4 blocks. The first 2 are about filter definitions that work in a sense. So the first one is about parameterization invariant, which is the idea that physics should be invariant under, so should be independent of the coordinates that you use to parameterize your field space. The second one is something less trivial, let's say, which is the fact that there are some observables that remain invariant under filter definitions. We will see that this is not the case for all observables. And this is closely related to the LSZ formula in the quantum case. I will give a classical version of that. And then the two last blocks, be shorter, will be about what issues you have when you do a filter definition that's not valid. And by valid, I mean, I will clarify in a moment, but essentially it's the fact that the filter definition has to be a one-to-one mapping. If it's not, then there will be issues in general. So let's start with reparameterization invariance. Just to make it clear, the idea here is that you have your action, which depends on the fields, but the field phi that you choose is just a coordinate in field space. You could choose another coordinate, let's say curly phi, and the action that you get by replacing that should give equivalent physics, right? It shouldn't matter what field you're using to parameterize your configuration space. This is true, but it should be noted that F must be a one-to-one mapping, right? If we're thinking that F is a change of coordinates, then it must be a one-to-one mapping. Otherwise, you lose parts of field space or you duplicate them. So we came up with this maybe more precise definition of what's a valid filter definition F. So we call it an interpolating field. And we say that F is an interpolating field whenever its functional derivative is non-singular. That means, so this in general, it's an operator. And that means that when it acts on test functions, it should give 0 if and only if the function itself is 0. And I have some examples on the right here. So the first one is just the filter definition, the identity. The functional derivative of that is 1. It's the identity matrix, and that's a non-singular operator. In the second case, I've chosen f of phi equals phi squared. And then the derivative of that is 2 phi. And that means that for phi different from 0, you will get something that's non-singular, but for phi equals 0, this differential operator becomes singular. So in this case, F would not be an interpolating field. And a final example, you can also have an F that depends on derivatives of phi. It doesn't need to depend on just on the value of phi. So I have box phi here, and then the functional derivative is the box operator. And that itself is also singular, basically because you can have functions that are non-zero such that their second derivative is 0, right? This is the Klein-Gordon equation for a massless field. And there are non-trivial solutions to that. So that's an interpolating field. And that means that locally an inverse to this mapping exists. And if it exists locally for all values of the field phi, then exists globally. So this is just a local way of expressing that F is globally one-to-one. And the name interpolating field, which might seem maybe strange, is just taken from the QFT context, in which you have interpolating fields in the LSZ formula, and those are the ones that create states when acting on the vacuum that have non-zero overlap with one particle states. And we show in the paper that if you have an interpolating field in the classical sense that we've defined, then you have an interpolating. If you quantize the theory, you have an interpolating field in the quantum sense. But this is a purely classical.
Sorry to interrupt you. I have a small query. So will this work when the f of phi is, for example, like a mapping is not, we have mentioned one-to-one, but for example, the f of phi is like a square root of d square operator, with a kind of
square root of
d square. I mean, for example, if you talk about the harmonic operator, and you can look for the bosonize as a d square, but that's just d square to the power half. You can think of that way. So on those context, for the harmonic case, is it guaranteed that we will have the interpolating field?
I don't think, yeah, in general, I don't think so.
Mhm.
I mean, I would need to look at it in detail, but yeah, I mean, if there are square roots involved, in principle, it's not one-to-one. But there's a loophole in here. I was just about to mention. Maybe this also clarifies a little bit that. Because so there are two ways of I see a hand raise.
Yeah.
Yeah, a small query. In the previous slide, the box operator, if
Yeah.
it's constructed from gauge covariant derivative and at some order of perturbation theory, the gauge field is mixed with phi itself, then will it be always true that del f del phi equal to box?
Can you repeat the last question? Sorry.
So let's say the box operator is constructed out of gauge covariant derivatives. It contains
Right.
the and
Let's say it's d squared, no?
yeah, d square.
Mm-hmm.
Yeah, and let's say at some order of perturbation theory, the gauge fields are sort of coupled to the scalar field phi itself, so that
Right.
the box operator itself contains the phi's. It might happen, right, under renormalization of these operators.
I mean, classically it wouldn't happen, right? Because
Classically, it
there's
wouldn't
no.
happen. Yeah, I completely agree. But let's say when you're doing field redefinition and applying it for computing expectation value of quantum mechanical operators, which is your last line,
Mhm.
then it might happen that the box operator itself contains the phi field itself. And will it always true that del f del phi equal to box? It may not be, right?
It can be, yeah, it will depend on phi too.
Okay.
My guess would be that even in that case, it would be pretty clear that this is not an interpolating field, because at least you will have a term which is box, and then plus things that depend on phi.
Correct.
And that's a differential equation that you can probably solve with some non-trivial solution.
I see. Okay, thank you.
But yeah, so there's a way to escape, in a sense, this. So there are two ways of building interpolating fields. One option is that the functional f is ultra-local. By this, I mean that it only depends on phi and not on its derivatives. So it becomes a small f, which is a function instead of a functional. And it just needs to be invertible. And then you can have an example like this one, right? But you can also have redefinitions that include derivatives, maybe going to that point. And that's the second option here. So you can have a field redefinition that has, typically, this is just phi, but you can have something more complicated as long as it's an invertible function of phi. And then plus a small parameter times an arbitrary operator. And in here, you can have something that's not invertible, square roots, derivatives, etc. As long as lambda is a small parameter, and you expand everything in the theory as a series in lambda, this is a valid filter definition. Why? Because it's invertible as a power series, right? So as long as lambda is a small parameter and you only do perturbation theory with it, it's not allowed to put lambda in something non-perturbative, then this should also work as an interpolating field. So those are the two ways in which you can construct interpolating fields. And the second one is the one that we usually employ in EFTs, right? We have some, so lambda again is 1 over the cutoff scale or 1 over the cutoff scale squared. And then the definitions that we do are phi plus lambda times high dimensional operators, or whatever you need in there to cancel the operators that you want to eliminate. All right, so those are interpolating fields. And now that what I will assume for these two first blocks is that the field redefinition is it gives you an interpolating field. So the F in here is an interpolating field. And whenever that happens, everything works pretty nicely. So let me show first that that physics is indeed invariant under this kind of redefinition. So I've written here a generic action with a source term, and that will be useful later on. And then the redefined action with the redefined source term. So just you take the original one and you plug in f of phi. And the classical physics that, right.
A quick question is, with any interpolating field, the Jacobian or the source term, what happens to them with a generic interpolating field?
So yeah, so the Jacobian should be non-singular. This is essentially what I was saying. In quantum theories, there will be a determinant of the Jacobian in the path integral, and that can be non-trivial. And in that case, you need to introduce ghosts in the theory to let's say to take into account this determinant. In practice, if you have a redefinition of this kind, so a perturbative one, and you use dimensional regularization, then all those ghosts decouple and the determinant is not relevant. That's in that particular case. I see another hand, maybe.
Yeah, in the am I audible?
Yes.
In the same context, so the Jacobian in dimensional regularization, if we consider up to dimension 6, so the Jacobian is 1, right?
Yes. In dimensional regularization. Yeah.
And you are saying that if we consider, is it that if we consider higher dimensional operators other than dimension 6, so what happens to the Jacobian then?
It shouldn't matter, I think. The redefinition can be, so if you have dimension 8 operators, you will have something more complicated in here, right? You will have high dimensional operators in the redefinition. But as long as it's a perturbative one, the Jacobian will be 1.
I have a related comment on that thing. That when you're defining this H, so if your H is basically only polynomial in fields when there is no derivatives, for example, as you are mentioning, that if I restrict myself to dimension 6 only, then I cannot have more than 2 derivative terms, right, in the effective operator. So your H is basically only polynomial in fields, right?
Well, even at dimension 6, you can have d squared phi squared.
No, d squared phi squared, but when you absorb in the kinetic term, the Jacobian, when you calculate, the Jacobian is only function of fields. There is no derivative.
All right.
From the field definition, because the field definition doesn't include the derivatives there in the dimension 6 level. So, and as you have mentioned, that if I exponentiate that Jacobian using the kind of a ghost action, so that will mimic some kind of a non-trivial contribution, but like a static ghost. And then in the dimension regulation, you can decouple from them, right? That's what you meant.
That's right.
But I'm wondering that if I go beyond dimension 6, I don't know whether you talk about that thing, then in the Jacobian, there could be some derivatives, and those ghosts can be a propagating degree of freedom.
Right.
So then, how will you talk about that thing later? Something later?
No.
So that is my query actually, because that's what I'm trying to also understand. That if I go to dimension 6, the ghost become propagating degree of freedom, which will appear in your off-shell S matrix and all those things. So how you deal with them?
Right. So I think there are two ways to see this. So maybe there's a more intuitive one and maybe a more precise one. But so if you have derivatives, let's say, in there, then something that you have is you have derivative squared over lambda squared, for example.
Yep.
Right?
Yep.
If you and that's the kinetic term for the ghosts, essentially.
Yeah. Yeah. Yeah.
If you canonically normalize that, the lambda square goes to the mass term for the ghosts.
Okay. And
so those have mass lambda,
yeah.
and then they decouple.
That's
this is the intuitive.
This is the intuitive. Yes. Okay.
And maybe I prefer the second way, which is just the fact that we're in EFTs we are restrict. So we can only do perturbation theory in 1 over lambda. We can never have something in which lambda appears in another way. So if you have 1 over lambda in front of the derivative terms, even if those are quadratic, you should treat them as an interaction.
Okay.
So you have Feynman diagrams with a trivial propagator for the ghosts, and then interactions in which you insert the d squared.
Yes.
And that's 0-dimensional regularization.
Okay. Okay. We agree on the second note. Yes, I prefer the second one also. Okay, great. Thank you.
Great.
Just a quick confusion. I might be wrong, but if I have derivative field, if I have some derivatives in the field redefinition, wouldn't I generate some non-local operators? Because when I take inverse of that,
again, so that you can only have derivatives if they appear as a perturbation, and then you can invert this relation as a power series in lambda, and that will be local too.
Okay, I see. Okay. I see. Okay. Thank you.
All right. Thanks for the questions. These are all very interesting to me. I have another older paper in which I discussed it with Manolo Perez Victoria. We concentrated on a little bit different things on this one, but if you have any other questions about this, I'm happy to discuss. All right, so I think we've clarified a little bit this definition and the idea of the interpolating field. So we have here two theories related by a field redefinition, and all the physics of these theories is since they are classical, is contained in the equations of motion, right? So I've written here the equation of motion for the original theory on the left and for the redefined theory on the right. And we're going to see easily that they are equivalent. So first of all, you can apply the chain rule, and you will then have these two equations. So the equation on the left is now the derivative of the field redefinition of the inverse of the field redefinition, g is f to the -1 times the redefined equation of motion and the opposite thing on the right. And now, just because these operators are invertible, they are non-singular because we have an interpolating field, then I can essentially cancel these things, and I end up with these two equations, which have change signs, right? Now I have the equation of motion for the redefined theory on the left and the equation of motion for the original theory on the right. So they are equivalent. And what we have here is that a solution to the original theory generates a solution to the new theory through the inverse of the field redefinition and vice versa. So you can go from one to the other, and the physics are then equivalent. So fine, the physics is equivalent, but obviously the solutions that you get are not the same. So if you are able to measure the value of the field, for example, itself, you will get different answers in one theory and on the other. So let's say you have a magnetic field that you can measure. You measure in one theory, you do the field definition, you won't get the same result in the other theory. the two results will be related by the filter definition, but they are not the same. So, and this is a broader point about observables in general, right? So you have any observable that it's essentially a function of the solution to the equations of motion. For that observable to be the same in the redefined theory, you have also to redefine this observable. And maybe an example that's more useful for the quantum field theory application is looking at green functions. So if you look at the green functions of the original theory, they will only be equivalent, or they will only be equal to the green functions of the new theory. So computing with S hat now, but having here the F applied to phi. And in general, you won't have the relation on the bottom, in which you just naively put in here the redefined field. Yes, question?
Yeah, I have a question that after field redefinition, if you write down the Hamiltonian of the theory in terms of the new fields and try to solve the vacuum of the theory, what guarantees that under field redefinition, the vacuum remains intact?
I would say it can change.
Okay.
It will be the F up or F to the -1 applied to the original vacuum.
I mean, and from classical equations of motion, you expect that. But when you're trying to do quantum mechanics, you should separately solve the theory to determine the vacuum, right?
Right. This I don't know.
Okay.
Yeah, I'm not sure about that.
I mean, since you're talking about Green's function, it's the vacuum expectation value of time order operators.
Right. I have an alternative definition for that.
Okay.
In the classical sense, which I will explain in a moment.
Okay.
And in that sense, it's true what I'm writing here. If you write vacuum expectation values, it might not be so clear, at least in the let's say in the canonical picture. I would say so if you think about path integrals,
yes,
and correlators inside path integrals,
right,
it's clear that this is also what happens. But if you look at the vacuum, right now, I don't know.
Yeah, but also in path integral formulation, if you solve the Euclidean theory and go for large beta limit where only the ground state contributes, and if you want to solve the Euclidean theory for two different phis, like before and after field redefinition,
All right.
it's not trivially guaranteed that the vacuum state you will get from the old set of fields and the new set of fields are identical, right? So it's probably, it has to be done and checked for case by case, I guess.
I guess so. Yeah, I'm not sure at the moment. Yeah.
Okay.
But yeah, so at least, yeah, in the classical sense, in the classical case, it's clear that this is what you get. I will show an example in a moment. But yeah, this is just to make it clear that you have to redefine observables. This is maybe a bit trivial, but it's what we do when we do field redefinitions in EFT is, in a sense, what's in the red box. Only instead of green functions, what we compute are amplitudes. And it turns out that for those, there's an equality here, even within the observables. Those are observables that stay invariant under field redefinitions. They don't need to be redefined. But I will talk about that in a moment. I'll just show an example now, a very simple example, a harmonic oscillator. So 1 time plus 0 dimensions in space. Yeah, so the action is just harmonic oscillator. And then I consider so there's a source term, and then there's a field redefinition, which has a derivative here. So we have to keep in mind that lambda is a perturbative parameter, and we have to do perturbation theory. As long as we do that, we should get the same physics as we've seen. And this is what we get. So this is the solution to the original theory. and this is the solution to the new one. And you can explicitly check that applying the filter definition to this gives you what's at the top, and the same to the other side with f to the -1. But obviously, as I was pointing out earlier, x and y are not the same. So if you measure x, you will get the same result as if you measure y. You will get the same as if you measure f of y. All right, so that was about parameterization invariance, and now let's see what observables are invariant under filter definitions. So you don't need to do this extra step. So the situation we have, I've just written again what we had in the previous section. So we have some action with some source term, and if you think about it as only being able to measure the field phi externally through the source j, then all observables will be essentially the functional derivatives of Sj with respect to j. So I'm writing them in this form. Then I have the redefined action, and naturally the observables that come from this, since I've redefined the source term, will be the redefined observables. So they will be the same in the two theories. But I now want to compare this to a theory in which I have the redefined action, but the source terms, for them, I just do the naive thing. So I just couple the source to the new field and not to f of phi. And then, as I've said, the observables are different. What we really need here is to check for observables that, for the same action and different sources, give the same result. So this is the filter definition. You do it from the first line to the second one. But we're really interested in the step from the second one to the third one. So having the same theory, but with different sources. And a nice example of this, I think, is the driven harmonic force. Your solutions will be some oscillations with an amplitude, and that amplitude has a pole when the driving force oscillates with the resonant frequency of the oscillator, right? So in general, the solution depends on what driving force you have, on what source you have, but close to the on-shell limit, so near the resonant frequency, this behavior becomes universal, and it doesn't depend on what source term you have. As long as the driving force has a frequency near this, you will have 1 over e squared minus omega squared as the dependence on E, and then some amplitude, some normalization factor at the top. And this is exactly what happens also in field theory. So the observables that you have that will be independent of the filter definition or independent of the source term will be the positions of the poles of the green functions, or even of the field solution itself, as we will see, and the residues at those poles, which are trivial in the case of the harmonic oscillator, but in quantum field theory, they are the amplitudes. The scattering amplitudes, let's say. Okay. So yeah, so what we did in the paper is since we were doing classical field theory, we wanted to have a classical analog to the LSZ formula. And this might seem maybe trivial because we all know that quantum field theory at tree level is classical field theory. But if you look at it in detail, it's not so clear, especially because for the LSZ formula, you have scattering amplitudes, which involve objects such as asymptotic multiparticle states, and those are inherently quantum things. So the best you can do with that is a semi-classical approximation. So we try to do something purely classical, and I think it's a nice exercise. I think maybe it clarifies things and gives an alternative proof of the LSZ formula at the classical level. So the setup is what I've written already, the action with a source on the equation of motion. And apart from the picture in which J is the only way to measure the field, you can also think, so the only way to act on the field, you can also think about it being the measurement apparatus. So it's the only way that you have to measure the field itself. Then the only things that you can measure, so J is like, I don't know, the needles or the numbers in the measurement apparatus. The only thing that you can really measure is the self-interactions of J once you integrate out phi. And classically, you can just do that. So you have an effective action, which depends on J. This contains the self-interactions of J, and those are your observables. And this is just the action evaluated at the field solution. So we want to see what happens to the field and what happens to this effective action near these poles. What you can do is you can expand these two things, so the field itself and the effective action, in powers of J. And then you have these coefficients, which I've named in this way. And this is the definition for those green functions that I've written before. So the coefficients of the expansion of these two functionals of J are what I'm going to call the classical version of the green functions. You can check that they are indeed related at the classical level to the quantum green functions that you define with expectation values. Okay, so we are going to look at these objects and see what poles they have. And these are so we proved these two theorems in the paper. The first one is about the coefficients of the expansion for the field. And what happens is it has poles when each of the external momenta go on shell. It splits in this way, so it has normalization factors which depend on the source term, one for each external momenta. And then you have this part here, this factor, which is the amplitude, and that doesn't depend on the source terms. So this only depends on the action, on the action of the theory. So this is the result we were looking for, right? This is independently of what F is, the poles will be at the masses of the particles, and if you strip off these normalization factors, these Z's, you get an amplitude that's independent of the source. Okay, I guess that's all. There are some details about this. So, for example, Z is just a polynomial in the momenta, but essentially that's the idea. And then we have a very similar theorem for the coefficients of expansion for the effective action. So these are the coefficients of the self-interactions of J, which are essentially the observables that you will have. And they also split in this way. There are some assumptions for this, which I think are worth mentioning. So we assume, obviously, that the action is local and that F is an interpolating field. More non-trivially, we assume that the background field is 0, at least it's constant, and you can always shift it to be 0. If it's not, we don't have any results, but it's a direction we're exploring. So what happens when you have non-constant background, for example, in gravity or a soliton background, something like that, then this might change a lot. And then the other assumption is that the linearized equation of motion is the Klein-Gordon equation. This is because it's a scalar field, otherwise it would be the Dirac equation or whatever. It matches the spin. But yeah, this is, I think, a reasonable assumption. It's the place from which these poles in p squared minus m squared come from. So again, let's see a very simple example. Again, I'm just a mechanical one. Yes, please.
Yeah, about this equation of motion being the Klein-Gordon one. So in general, if you are looking into correlation function, they should satisfy Dyson-Schwinger equations in quantum field theory, right? And now we are
Right.
talking about the 2-point function here. Now, if I try to solve the Dyson-Schwinger equation for the original field and the redefined field, and then take the classical limit, is it guaranteed the canonical form of Klein-Gordon equation will be retrieved?
I'm not sure about that. I haven't thought about it.
Okay.
Again, in the classical case, we've checked that this is
Yeah, I mean,
how it works.
it's an expectation, right? It should come to the
It
same.
should. I think so. I mean, so there's something I haven't mentioned here. There's something else in here, which is that if your redefinition is perturbative, it might add extra things into the quadratic part of the action, and then you can have some momentum dependence, which is not the Klein-Gordon equation.
Right.
But again, this is thinking about perturbation theory always. So as long as this is a small parameter, it works.
Yeah, I mean, I had a question in mind in the same context. Like, if you compute the spectral function of the theory, whose poles give you the physical masses, right? And now, let's say I want to compute the spectral function of the theory with the old definition of the field and the renewed definition of the field, and try to solve the field theory. So probably at classical level, the poles will appear at the same places, but again, after quantum corrections, the location of the poles might shift up to some order of the perturbation parameter, right?
I mean, it will shift in both theories, right? And it will shift by the same amount, I would guess.
Yeah, the question is, will it shift by the same amount in old fields and the new field definition of the field theory? That's the question.
Right.
So Juan, if I may interrupt at this, in this point. So this, when you have the older definition of the field, and when you do this field definitions with the new fields, okay. So the only shift through the time order of the Hamiltonian, if we do, there's only shift at the action level. So your action will have some additional contribution, which is basically imaginary part in the new contribution in the action, and which does not affect our observable. So all the spectrums and all those things will be invariant.
I'm not sure.
No, this can be computed actually. I mean, this can be computed, and that additional contributions, when you calculate the quantum corrections, they got cancelled order by order. Because that term you cannot have, because those terms are basically very large divergent terms that you will generate between these two theories. Maybe we can talk about this after the talk.
Yeah, I need to think about it a little bit. I would think at the quantum level, it shouldn't change the positions of the masses, but
no, it doesn't change.
All right. So I was just going to show an example of how this works at the classical level. So again, going to mechanical example, but now it's not just to make it non-trivial. There's an interaction, so it's not only the harmonic oscillator, but there's some x squared term, and there's the theory with this action and the trivial source term, and then some new source term, which is more complicated, right? And there's derivatives, and there's an x squared. And we can see here explicitly how the green functions change. So the first one here, the orange one, is the one for the 3-point function for the original theory. Then it's pretty trivial. It has the poles that you'd expect, and then the amplitude is just g. And now you can look at the 3-point function in the redefined theory, And in that case, you get one term with the correct pole structure and some factors which correspond to the normalization factors Z that I defined before. And then some extra terms. And this, so the fact that the energy appears in here is due to the fact that the field definition contains a derivative. And the fact that you have these extra terms in here comes from the fact that the filter definition has an x squared. And then that means that the source, or let's say the source term has an x squared. And then the source has two legs. There are sources with one leg and sources with two legs. And there's those give all these three extra terms that I have in here. But you can see that in the on-shell limit, all these other things disappear. Only the first term dominates, and then it has the poles that so the same structure as the first one. And if you divide by the normalization factor to the third power, you get the same thing. You get the same amplitude, which is just g in this case. So that's the general statement about the functions. That if you remember, I had an equation in which I had this on the left and this on the right, but there was a not equal sign in between. And now these two things are equal asymptotically as you approach the on-shell limit if you normalize both things. So you need to compute the z, for example, from the 2-point function. Once you have it, you know how to normalize all the other higher point functions, and they should be the same on-shell. All right, so that's the statement that amplitudes are the definition invariant. And just a very brief point here that these classical objects that we've defined, we show in the paper that they can pretty easily be related to the tree-level approximation to the quantum analogs. So at tree-level, this expectation value is the same as the green function I've defined. And then from the Canel-Riemann representation, you can, and from the one of the two theorems I've shown, you can derive that this overlap of one particle states with the states created by the new field is the normalization factor that you have in here. So that relates interpolating fields in the classical and the quantum sense. And then if you compare the classical LSZ formulas I've given and the quantum well-known LSZ formula, you can see that these amplitudes that you define in terms of the infinite past and the infinite future are at tree level are just these objects that I defined classically in terms of the poles of the classical green functions. So that's the connection with QFT. So in a sense, we've only given an alternative proof for the LSZ formula, but also a more precise definition of what it means to do these things purely classically, and not only as a classical limit of a quantum theory. All right. So that finishes the first two blocks, and now I'll talk a little bit about the issues that you will have if the field definition is not an interpolating field, so if it's not a one-to-one map. So let me start with an example, going back to the harmonic oscillator and the same redefinition we had before with a derivative and a parameter lambda. But now let's say I forget about this idea that lambda is a small parameter, and I don't want to do perturbation theory here. I want to compute things as functions of lambda, arbitrarily complicated functions of lambda. Then the equation of motion of the redefined theory does not only have the two original solutions that you could get in perturbation theory, which are oscillating, but you also get two new solutions, which are clearly not perturbative in lambda, right? They are exponentials of plus or minus t over lambda. So you can expand that in powers of lambda. So there are new solutions to the equation of motion if you have this kind of field definition and you don't take care of doing perturbation theory. And And the reason why that happens is the following. The new equation of motion is just the original one with some differential operator applied to it. So whenever f has derivatives inside it, it will act with derivatives on the original equation of motion and will turn it into a higher degree equation. And then it will naturally have more solutions, right? So we classify the types of solutions that this can have in two kinds. There are physical solutions, and those are the ones for which, if you apply the filter definition, you obtain a solution to the original theory. So they don't change the physics in that sense.
So what can you remind me that S hat was the redefined after the Philippine action, right?
Yes.
Okay.
Exactly.
Thank you.
So this is the redefined equation of motion, and
that's why
it has higher degree.
Del F by del phi is coming up with the redefined.
Sorry?
And that's the source of this additional term, del F by del phi. Okay.
Yeah, exactly. Yeah.
Okay.
So the S hat is S of F of phi. Then you apply the chain rule, and you get this.
Yeah. Okay. Thanks.
So it's a higher degree equation. You have physical solutions, and those because it's a higher degree equation, you can have multiple solutions that correspond to the same solution in the original theory. So you can have phi 0 and phi 0 prime, and F applied to both of them can give the same field in the original theory. So there's some duplication in there, but at least they don't change the physics. And then there are other solutions which are unphysical, or we call them physical because they give different physics than what you had in the original theory. And this happens in the example I just showed. I will go back to that in a minute, but we can do some counting, at least for the degrees of these equations. So I'm denoting here by the x the maximum number of derivatives that appear inside x. So for example, if x is the action, then this is the maximum number of derivatives that appear in any terms, that appears in any term of the action, and it's also the degree of the equation of motion. And the same goes for f. So we derive some formulas for this, some bounds on the degrees of this equation. Maybe the nicest one is this one. So if the original action does not contain linear terms in phi, so it's quadratic or higher, then you get that the degree of the redefined equation is greater than or equal to the degree of the original equation plus 2 times the degree of the filter definition. And this relation is saturated when the action is quadratic, and you have an equal sign here. So let's apply that to the example. So the original equation is a harmonic oscillator equation, has degree 2. And the filter definition has one derivative, so it has degree 1. So the degree of the new equation, this one, is 4, and that agrees with the formula I've just given. So indeed, we have 4 solutions, as I said. 3 of them are physical, and those include the 2 ones that you could get in perturbation theory, and also the e to the minus t over lambda, which, if you apply f, gives the trivial solution in the original theory. So that's also a physical solution in that sense. And then there's the unphysical one, which, if you apply f to it, gives you something that's not a solution to the original theory. And that, therefore, that's new physics. Okay, so we've seen that if we apply a filter definition with derivatives in this way, and we are not careful about doing perturbation theory, we get new physics in the new theory. So that's not allowed in principle. There's a way, so if you insist in trying to do this, we try to see if you can fix it in some way. And we found that you can recover the original theory by using boundary conditions, by adding some new boundary conditions. And the idea is maybe it's better to just look at the right column in this table. So so we have, yes.
Yeah, I have one just a small suspicion that whenever we talk about the field theory, the quantum field theory in a manifold, I mean, we generally do not consider any kind of boundary because, I mean, we just asymptotically there to be zero, right? So and that's why we don't put any kind of boundary conditions. But here, if you put some kind of boundary conditions, I'm wondering whether some effect of the boundary operators and those things can be popping out in your picture or not.
So this part, I'm really not sure. So I guess you could think about boundary conditions for the path integral.
Because that is the one thing actually I'm encountering recently. For example, for the harmonic field theory, when we do convert them in terms of bosonic theory, in the process, actually though you start with a quantum field with no boundary, but then you create basically boundary, and that leads to some kind of Chern-Simons terms on those kind of things. So that's why we refrain ourselves to put no boundary conditions, because the field just in the asymptotes, we just allow the field to die out just like that. So imposing any boundary condition will in turn, because then I cannot remove the total derivative terms and all those things, and they can lead to some kind of operators, right? I mean, that's what my assumption about this thing.
I must say we haven't thought about the quantum case in detail for this at all.
Okay.
I'm thinking about boundary conditions in classical field theory, which let's say initial conditions for your field, for example. But in the
Okay.
I can't say anything about the quantum case. So.
Okay. Thank you.
But yeah, at least in the classical theory, it's so what you have is this: you have your original equation of motion applied to the redefined field. So this is the harmonic oscillator equation, the blue part, and then some differential operator acting on it, coming from the field redefinition, and that's the orange part. And the reason why you get unphysical solutions here is because the fact that there's the orange part in here does not guarantee, so it makes it so that it's not guaranteed that the blue part is zero, right? Because there will be solutions to the second row in the table, which is just the orange part, the differential operator acting on some function. If there are non-trivial solutions of this, then the original equation of motion itself could take that form, and then it would be non-zero, and then that's a non-physical solution. So that's the idea, and the way in which you can solve that is by, so if you want to make sure that a solution to this equation is trivial, you have to impose that in this case, it's just an initial condition, that the initial condition is that the derivative of this function is zero. And if you impose that and you have a first order equation, then the solution must be zero everywhere. So this is in general what you can do with this kinds of physical solutions. You can impose that the derivative, in this case, at t equals 0 of the original equation of motion is equal to 0. So this is a boundary condition, and that eliminates only the unphysical solution that we had and leaves the other three physical solutions in there. So this is a fix for the problem that we had, but it's extra information that you have to provide. So it's not ideal at all. So now you have your theory, you do a field redefinition, and you cannot only give, so it's not only defined by the new redefined action, but it's defined by the redefined action plus some boundary conditions that make sure that you get the same solutions as before. Yes, question?
Yeah, so this unphysical sort of boundary condition which you used to remove the unphysical solution, initially when you put the partition function which had the path integral measure, they had all possible field fluctuation. So do you introduce an additional delta function for imposing this boundary condition, or how do you do it?
Right. This is again what we were saying just in the previous question. We haven't thought about the quantum case in detail.
Okay. Never mind.
At the moment I can't say anything. Sorry.
Okay.
All right. So final part, this will be short. So we've seen field definitions that change the equation of motion, but there are also field definitions that change the field space itself. And an example, very simple example, is this one. So I've chosen here a field theory in one space plus one time dimension. And the field definition is phi goes to phi plus phi squared. And then you can see essentially for values of the original field that go, so that's the y-axis here, that go above -1/4, you get two inverses. So there are two possible values of the new field that correspond to that. And if you go beyond -1/4, there's no possible value of the new field that recovers that. So any solutions of the original theory that go beyond that, you already lose them by doing this field definition. So that's something that can happen. You can lose solutions by doing this. And you can also get new solutions. And essentially the idea here is that you are changing now the potential that you have. Originally, it was just phi squared, but now it becomes a double well potential, and there can be solitons that connect one side of the double well to the other. So very briefly, so solitons are static solutions that with finite energy. In the original theory, we don't have any solitons. We have two static solutions, which are exponentials to one side and to the other. Set here is just the space component of x, and there's no time dependence on these solutions because they are static. So you have these two static solutions, and they have infinite energy because they diverge either at plus infinity or minus infinity. However, in the new theory, you have solutions of this kind, which connect one minimum with the other. And you glue them together at this. So the part that comes from this, which corresponds to the set to the e to the minus z, with the part that goes like e to the z on the other side, and they glue smoothly in between, and they have finite energy. So these are static solutions with finite energy. So this is a very clear difference between the two theories, right? One has solitons and the other doesn't. If you try to transform this back into the original theory, you get something like this with a cusp, and that evolves in time, right? That will tend to dissipate to the sides. And the last point is, if you try to fix this with boundary conditions by imposing that at both sides it goes to 0, for example, to one of the two minima, you will still get multi-soliton solutions, which are again at least approximately static, and those do not appear in the original theory. So even with this cannot be fixed with extra boundary conditions as it happened before. And that's all. Let me conclude by summarizing very briefly what I have said. So we know that physics is invariant under field definitions, but they must be one-to-one mappings. Observables are not invariant, but you can redefine them and you will get the same physics in the end. And then there's the particular case for amplitudes, which are poles and residues of Green functions, which stay invariant without having to redefine them in any way. Then what happens if you do things that are not one-to-one? You will get new solutions, and some solutions will disappear. Some of the new solutions will be unphysical, and they can be eliminated with boundary conditions, and some of them will be unphysical and you won't be able to eliminate them with boundary conditions. So suddenly you have new things in your theory. And yeah, some outlook and maybe some related to some of the questions. Something that we are looking at is what happens to the path integral when the field space changes, for example. So when you have a definition like the last one, now the path integral grows from plus infinity to 0 and back to plus infinity, and it seems that the path integral would be 0 directly. So yeah, we need to understand that. And then it would also be nice to understand better the interplay between field redefinitions and renormalization, anomalies, etc. So in general, looking at now the quantum effects. And yeah, that's all. Thank you very much.
Thank you, Juan, for this wonderful talk. Yeah, so now the session is open for the questions. Yeah, Devtosh, please.
Hi, Juan.